Good evening, everyone, and welcome to Westmoreland Geological Society's winter lecture. Tonight, we are fortunate to have with us Dr. Hugh Tuffen from the University of Lancaster. Hugh is a volcanologist who uses a combination of fieldwork, geochemical analysis, experimentation, and modeling to investigate key eruption controlling processes in volcanoes. He completed his undergraduate geology degree in Cambridge. He then did a master's at Clermont-Ferrand and a PhD at the Open University. He completed several postdoc positions before taking his current job at Lancaster University, where he's a lecturer. His current research interests include investigating how gas escapes from highly viscous silica-rich magmas, and how can we exploit magmatic heat to generate powerful geothermal energy. This evening, Hugh will be talking to us about looking inside volcanoes. So I would like to hand over to Hugh to give us his lecture. Thank you.
Whether anyone who's here tonight has been part of the Cumberland Geological Society. I probably shouldn't mention this bitter rival of WGS. It's just that we went to Iceland in 2003. I can't believe that 17 and a half years ago that we had 10 really fun days going around Iceland with fantastic weather. If there are some of you, then I remember that trip with a lot of fondness, and we'll probably see some familiar rocks shown in the slideshow tonight. We're going to be looking at Icelandic volcanoes. We're going to start off having the big picture, a bit of tectonics and the overall setting of Iceland. And then we'll look at basaltic eruptions, but that's frustratingly shallow. We're going to be looking at eruptions of basalt just on the surface. And it'll be giving us the urge to try to dig down deeper, which we'll do by going into rhyolitic volcanism, to this high silica, highly explosive side of things. And we're going to gradually mine our way down through the Icelandic crust and see what we find as we do so. So that is the plan for probably about the next 45 minutes. But if I start talking on too long and you need to be going, then please just prompt me, Richard, to keep ticking things over. This is work that I've had the pleasure to be doing for a long time. My first trip to Iceland was in 1996 as a field assistant for John McLennan, who's now in Cambridge, and we were camping and climbing up lots of volcanoes and sampling basalt. And then in 1998, I started a PhD working in Lancaster with Dave McGarvey, Jenny Gilbert, and Harry Pinkerton. I'm sure that some of you know these names. So I've been working in Iceland ever since, and I've kind of lost count of how many times I've been out there. It's an absolutely wonderful country. I'm guessing that quite a few of you folks have been to Iceland as well. This is research that I've been doing. I'm also talking about research that many other people have been doing, but my work has been done with a whole crowd of fun people, and some of them are listed there on this first slide, and we'll be mentioning people as we go through various different settings. Just a quick bit about me. Richard's given me a flattering and very nice introduction. Thank you. Just say that I'm a volcanologist. I guess you folks probably recognize that valley better than most people in the UK. So that's looking down Cromach, and you've got Grassmore, and that fell there is Low Fell, and I used to live just next to Low Fell, and I'm being fascinated why I could do much better skimmers on this side of the lake by Grassmore than I could on the other side by Red Pike. It was something about the rocks that made the skimmers much better, and that was the skidder slates. And I think that really set me off with having a lifelong interest in rocks. And I now do lots of teaching, like teaching geology, geological hazards, volcanology, climate change, even a bit of glaciology. And I've just been preparing a lecture today about deserts, which hopefully people are going to understand. And I have for about the last 10 or 11 years directed the MSc in volcanology at Lancaster University. So it's been great to see how many ex-students going on to so many great things in research in the geosciences. I've just put a bit of a compilation of recent Icelandic eruptions, and I'm sure that many of you are familiar with many of these. Some of you may even have seen some of these happening. So we had the kind of big players. This is since 1991, the eruption of Hekla. Hekla was active there. There was an ash plume and lava flows. In 96, we had this eruption of Gjalp, which is next to Grímsvötn under the Vatnajökull ice cap. And that was a big eruption that's created a lot of meltwater and flooding. Then we had Grímsvötn in 1998, Hekla in the year 2000. My friend phoned me because she was actually on the toilet at the time, and she looked out of the window in her farm in Iceland and saw this ash plume and called me straight away. Then Grímsvötn was active in 2004. So you'll notice that Grímsvötn is pretty active. And then we had Eyjafjallajökull in 2010, which took us all by surprise. We definitely didn't expect that volcano to be the next one to be erupting. And what happened with the ash plume and the impact on aviation in Europe was a very unlucky coincidence with the wind direction and the fineness of the ash that was produced. It was a good thing for me because I had an interview at the Royal Society the next day, trying to convince them to give me money to do research on Icelandic ash. And when I went for my interview, as soon as I walked into the room, they were said, here's the guy. I want to know how soon I can fly home. So I think that was an eruption that I should really be thankful for in terms of my career. That was then swiftly followed by Grímsvötn 2011. So Grímsvötn is a very active system indeed. And 2011 was a really big one as well, a huge ash plume. And then more recently, 2014 to 15, Barbabunga had a huge and spectacular eruption of lava, which was the biggest eruption of lava on Earth so far this century. We'll have a little look at that a bit later on. So Iceland is clearly very active. We've got our kind of main players like Grímsvötn and Hekla, which we see regularly going off, but no one really thought that Eyjafjallajökull or Barbabunga would be on this list of the recent eruptions, and we don't know what's going to come next at all. Just to remind you a little bit about Iceland, it is this expression of a mantle plume which first rose up about 60 million years more or less, and that was the volcanism which led to the opening of the North Atlantic, and we had the British tertiary volcanic province formed with those spectacular rocks in Mull, Skye, Ardnamurchan, etc. At the same time, there were igneous rocks being generated in Greenland. And then since then, the plume has been moving around, and it's now found where Iceland is currently located. It's the coincidence of the mid-Atlantic ridge with the extra mantle plume giving you more melting of the mantle than normal, which means you have thicker oceanic crust than normal, which sticks up higher than the sea level, which is the reason why we have an island. So it's the only part of the mid-Atlantic ridge that's sticking up above ground, if you like, out to the sea. It's very much an extensional tectonics, that the island is continuously being split apart, and it's kind of refilling in the center to heal this wound that is being developed. And this is probably a familiar map to many of you. This is the lovely map of the geology of Iceland. On the left and right-hand sides, these blue rocks, these are the tertiary rocks, which are older than 3 million years old. And these look very much like flood basalts. They're just stack after stack of basaltic lava flows. But as you go in towards the center of Iceland, you're becoming younger. So you're becoming less than about 1 million years. The pink stuff is less than 10,000 years. This is the Holocene, mostly lava flow fields. So you very much got a kind of rift that is opening up, and the very young rocks are all in the middle part of Iceland there. And we have particular different rift zones. There's the northern rift zone up at the north, the eastern one, and the western rift zone. This is the current position of the rift zones in Iceland, but these move through time. You can have jumps from one rift system to the next. The inferred position of the mantle plume is this big kind of orange coloured circle here. That's where the kind of highest proportion of melting of the mantle is taking place. And that corresponds with some of the highest mountains and some of the biggest eruptions too. And then we have a number of volcanic systems. They're called central volcanoes, is the organisation of much of the volcanism in Iceland. And this consists of a series of fractures, dykes, through which basaltic magma rises. And also there's a caldera, or there's kind of magma that's being stored in the shallow crust. And together, this is called a central volcano. So you can see some in the north here. This is Krabla. This is Askja system, which extends all the way from Vatnajökull ice cap, a long way north, all the way to the coast. And there's many other systems here. We'll visit many of these tonight. So that's the kind of basic important unit is your central volcano. Here's a schematic diagram from August Gudmundsson, the Icelandic structural geologist. And so we're looking here at a series of dykes. These are the fractures that are opening because the whole crust of Iceland is extending. And when you're extending, you're making a pathway that the melt that's generated in the mantle can then rise up through to form these dykes. But a central volcano is where the rising magma becomes stagnant and it starts to pool and brew and change its composition and can stay there for many tens or even hundreds of thousands of years and evolve towards a composition with much more silica of rhyolite. That's a central volcano. An example of a central volcano, I pointed out Krabla on the map from the north of Iceland. Here's an aerial view of Krabla. Maybe some of you have been here because it's next to the lake called Mývatn, which is a spectacular lake full of birds. Anyway, so this is the caldera of Krabla. This is a large depression which is formed when magma has been withdrawn in volcanic eruptions, and you have a depression that's forming like a piston going down. That's the main caldera, and then there's also this fissure swarm. So there's many fractures which are roughly north-south that you can hopefully see here. And some of those fractures opened in its most recent eruption from 1975 to 1984, called the Krabla fires. Very shortly after that, that eruption came just a few years after a new geothermal power plant was opened up in the caldera, because the caldera has shallow magma storage and there's a lot of heat. So there's a large geothermal area there, which is ideal to be sinking some boreholes and extracting high temperature fluids to generate electricity. This is one of the first plants in Iceland. And almost straight away, there was this fissure eruption taking place. They even had some basalt coming out of one of the boreholes, but it was only like about a bucket full. We think the smallest eruption in known history. Anyway, so this gives you an idea of a typical central volcano, that you have these magma-filled cracks which are parallel to the mid-ocean ridge. And then when you've got this kind of stalled, stagnating magma that's brewing away and changing composition, then there's a big heat flux to the surface. So that's where you can have your geothermal power exploitation. We'll go back to Krabla a little bit later on. In terms of seismicity, the Icelanders are fantastic earth scientists, and they have the Icelandic Meteorological Office does great monitoring of all kinds of geophysical signals, including seismicity. You can go to their website, weather.is, that is VEDUR.is, and then they're posting every single day kind of live the seismicity that's taking place. So if you've got a volcanological interest, then it's good to be tracking the earthquakes that are taking place. This is a view of all the seismicity in 2020 in the whole country. And it's clearly clustered here. There's areas that are more seismically active than others. And some of these are called transfer zones. So there's one up in the north here, which is where there's the kind of jump of rifting from one extensional zone to the next. This is like a strike slip zone where lots of displacement is taken up. Then you've got the main volcanic rift zones with lots of seismicity. And notice how many earthquakes there are, these little red dots in the central volcanoes. So for example, Katla in the north, in the south there, where my mouse is, in the very south, that has many, many earthquakes, and Torviokul just to the north of it. And there's many red stars, sorry, red, there's many green stars rather clustered together here in a volcano called Balverbunga, which we're going to be looking at very soon, which had this spectacular huge eruption a few years ago. That's reflecting having a large number of magnitude 5 earthquakes linked with the collapse of a caldera. And that is the seismicity this afternoon. So at the moment, nothing particularly dramatic is going on at all. There's no signs that any of the volcanoes are entering a seismic crisis that could be indicative of an impending eruption. So some of the questions that we're asking many questions, and this is just 2 very generic questions that we're trying to look into, is how do these volcanoes prepare themselves to erupt? And also what controls the violence of eruption once it has started? I'm not really going to be answering those questions tonight. It's fairly kind of, we're kind of deflecting those questions and asking many other questions, but those are the fundamental questions that we want to try to answer in order to help with the monitoring of hazards and to make sure that no one is harmed by these eruptions. And that's true in Iceland, of course, but much of the learning which is taking place from Iceland can be transferred to many other places on the Earth because there's such well monitored and observed eruptions that the insights from these can be translated elsewhere. So 90% roughly of the magma that's erupted in Iceland is basalt, this runny, low silica stuff. And these eruptions are fed by dykes, as I've already kind of mentioned. They're these fractures, kind of blade-like fractures, which open up. There's a seismic event. You're opening a fracture maybe a few kilometers in length, and then the basalt is rising a bit. These basaltic dykes, I'm kind of biased because I'm very much a rhyolite person, but they're reasonably dull to look at in the field. Probably people here absolutely love basaltic dykes, in which case I'm sorry, maybe the Scottish ones are better, but I personally never find basaltic dykes particularly fascinating in their own right. However, the patterns of dykes are very interesting because those tell you about the patterns of stress in the crust. And it was a dike that fed the eruption of Balverbunga from 2014 to 2015. This was a very large volume eruption of basalt, something like 1.5, 1.6 cubic kilometers. As I've said, it's the largest eruption of lava on the planet in the 21st century, and it's the largest Icelandic eruption since Laki in 1783. So here's a view of the erupting fissure, and there's this spreading lava flow field called Holohraun, which is being emplaced. Really spectacular stuff. So to remind you where we are, we're Balverbunga, we're here pretty much in the middle of Iceland. And there's an associated caldera. So there's one of those large depressions, the Balverbunga caldera, but it's completely filled by ice, by pretty thick ice actually, hundreds of meters in thickness. And people started to notice seismicity taking place in that caldera. And there was a depression of the ice surface, which just kept on going down day after day. So clearly, magma was moving out of that caldera, but where was the magma going? I remember watching, I was checking the earthquakes every hour because it was so fascinating what exactly was going to be happening in August 2014. This was clearly the kind of eruption that we've not witnessed in modern volcanology. And the depression on the ice surface kept on deepening. There was clearly a lot of magma moving underground. Unfortunately, at the time, the University of Cambridge had a team who were looking at microseismicity, so tiny earthquakes in the region, just a little bit north of where the eruption started. And this was with Tobbe Augustsdottir. And I'm going to show a video, which is an animation from some of her work, which is looking at the patterns of earthquakes, because the earthquakes were moving through time. They started off at this caldera, and then they started to move to the north east. So hopefully you two will be friendly to us and we'll play. There we go. So we're taking the first earthquakes now in early August, and just look at them. There's a swarm just moving through time. It's gone quite a few kilometers north, and now it's suddenly jumped, and it's jumped again, and it's always in these straight kind of blade-like lines a few kilometers in length. And then finally, this was the day when the lava came out of the surface. There we go. Isn't that a strange thing? So we've actually had magma that has been coming out of Bálðarbunga here. And rather than coming vertically upwards, as you might have expected, the magma has been going sideways by about 50 kilometers. And finally, it's come out at Hólmshraun, a long way away. So what was going on is that there was magma in the magma chamber beneath Bálðarbunga, and the pressure path was most favorable to have motion sideways rather than vertically upwards. And we had effectively pipe flow that was going on, and eventually the lava came out right at the surface here. This is a really big deal to have understood this kind of thing, and it means that if you look at a fossilized dike of basalt, not necessarily was the magma in it going upwards. It might have been going sideways. And so many people do magnetic work looking at the orientation of magnetic grains in dikes, and you could use those to try to infer the direction that the magma was flowing in. But it's such a spectacular example, this, of Bálðarbunga, of having this sideways magma flow. Notice that we haven't actually looked inside a volcano yet. We're using geophysics here and the patterns of earthquakes to infer something about how magma is moving. We're going to jump volcano now to Katla, which is a beautiful and huge volcano. She is the sister of Eyjafjallajökull, and she's the big sister. You can see from this aerial view here how much bigger Katla is than Eyjafjallajökull. And the Icelandic Prime Minister of the time, when Eyjafjallajökull went off and was causing so much disruption, said, "This is merely a rehearsal for when Katla erupts." So this is a very active volcano, very seismically active, very geothermally active. You could say it's the one that the Icelanders most fear, and it has a long history of eruptions taking place. This is a view here from the University of Iceland, this diagram showing the known position of some of the most recent eruptions. There was a fairly large one in 1755, which was once again in this caldera, this depression, which is ice covered in Katla as well. And then the most recent eruption that we know of, for sure, was in 1918, which breached the ice surface. There was a crisis in 1999 where there was much seismicity, and there might have been, and there was also melting of quiet. So there's the chance that this may have been a volcanic eruption too. I was camping about 20 kilometers north of there and was actually hoping that something would come out of the top, but it didn't. So the most recent major eruption was in 1918. And that's something that we've been studying in Lancaster. Jackie Owen had a research grant from AXA, from the insurance company. Jackie's still based in Lancaster as an earth scientist. And she was looking at this eruption. Why was it so powerful? Because it was an eruption of basalt. And normally, basalt isn't particularly explosive. It's that runny stuff that came out in Bálðarbunga, which doesn't tend to trap its gases very well. It tends to release the gases and be a good lava producer rather than a good exploder. But for some reason, the 1918 eruption was dramatically powerful. You can see the photo here of the ash plume that was taken, and there was a really powerful flood. The flood discharge rate was 300,000 cumecs, which is roughly the power of the Amazon. And it means it's one of the most powerful floods known on the entire planet in the last 1 million years. To put that to perspective, in Storm Desmond, the River Lune was the most powerful river discharge ever measured in England. And this was 150 times more powerful, this flood. So you can see the size of some of the icebergs that were being carried. That's me standing on top of a boulder that had been carried quite comfortably by the floodwater. So an incredibly powerful eruption. Why was that the case? Jackie looked at the ash that was generated in this eruption. The ash was, well, the vent of the eruption was here under the ice, and lots of the ash was washed down in this gigantic flood and created its own delta. It extended the coastline of Iceland, and you can see this black ash here because it's all basalt that came out. And Jackie did lots of digging in this ash and looked at the stratigraphy of it, and then looked in detail at the textures in the ash, trying to work out some clues as to what was going on. And what she noticed is that this is pumice, but basaltic pumice. And what she noticed was how strange it looked. It looked like a mosaic of little pieces that had been stuck together. We didn't really expect to find anything like that. This photo on the top right here is a thin section, so it's 4 centimeters by 2 centimeters. It's a thin section of one of these chunks of the pumiceous basalt, and it's just full of different color blobs of different densities and textures, all kind of fused and stuck together. And here's a microscope image that Jackie collected, and it's actually been blasted into really tiny pieces, only a few microns in size, which are then totally fused back together again. And so this was telling Jackie that there must have been a really extremely powerful explosions that were going on before the magma even hit the glacier. Because what we had always thought was it was explosive because the magma interacted with the ice and it melted it, and you had water, and then there was steam-driven explosions. But what Jackie found is actually no, this magma was already blowing up and exploding underground before it even felt or got close to the ice itself. And that's suggesting that it was a really gassy volcano, which in itself was quite a big surprise why Katla's so gassy. However, pretty much the same time, a paper came out from Evgenia Ilianskaya, who's based in Leeds, and she tracks aerosols and gases that come out of volcanoes. And so this team flew over Katla with a CO2 sensor, and they found colossal fluxes of CO2 coming out of some particular parts of the glacier that seem to correspond with these cauldrons where there's melting taking place at the base of the glacier. There's lots of heat coming up from underneath. This was such a huge CO2 flux, 24,000 tons per day, that it puts Katla as a new entry straight in at number 3 in the global chart of the biggest CO2 emitters for, as volcanoes. Obviously, humans would comfortably be higher than that. So this was quite something. Once again, there's a huge amount of CO2 coming out from Katla. And this is kind of a strange thing, because most of the high CO2 flux volcanoes, not all of them, but many of them are in subduction zones where there's a lot of carbonate rocks that have been forced underground and they're melting, and you're releasing that carbon that, say, was locked up in the limestone. It then gets released as a CO2 gas from a volcano such as Etna. So it's kind of strange to have this in a mid-ocean ridge setting such as Iceland. And what seems to be happening is that we have had subduction in the past, and we've forced loads of carbonates down into the mantle, but they have been hanging around there for a long time. So we've probably got some piece of old carbonate-rich mantle beneath Katla from a previous subduction event that we don't even know which one it was now. And I quite like that story, kind of showing that there's a kind of deep time frozen into the mantle, not only of the tectonics that we can see right now, but some older vestiges. So yeah, that definitely fits in with Jackie's idea that it's a very gassy volcano. Then things got quite fun. Peter Wynne, who's in the middle of the photo here, he's a glacial geochemist at Lancaster. And I got him kind of interested in Katla because there's a glacier that's very smelly called Solumjökull. It smells of rotten eggs every summer. And this was always kind of quite intriguing as to why it was so smelly. And Peter and our student Becca Burns got some samples of meltwater that was draining out of the glacier that comes from Katla. So this is a sample of the water that is from underneath the ice, close to where all this heat is coming out of the volcano. And measuring the composition of the water found much more methane than was expected. It's actually one of the highest methane fluxes that's ever been found coming out of a glacier. And the papers got in touch with us, and we had this rather silly headline from the Mail, as you may expect: is it the world's gassiest volcano? I was expecting this methane flux to be important in terms of climate, the methane flux from Katla, because it was so huge and bigger than anything that we'd ever heard about from a volcano or from a geothermal area or a glacier. However, I did some quick maths, and actually just the cows burping in Lancashire produce twice as much methane as this volcano. So from a climate change perspective, I think cows are rather more serious than Katla. But it's a very interesting story. And actually, this methane seems to be biogenic methane. It's actually microbes that are living in this strange environment between volcano and ice. They're being incubated by that heat. And it seems to be the microbes that are actually creating this methane, which again is a kind of strange idea, to have this giant great microbial incubator that's also a huge CO2 emitter. Anyway, Katla's a really good volcano. It's still a little bit frustrating because we can't get down onto the ground and really kind of look inside it because it's covered in ice. This is where I'll start to grin because I like rhyolite, this high silica stuff, and we can start to go underground now. Icelandic rhyolite, it's making up about something like 10 or 11% of the Icelandic shallow crust. It's these areas here which are marked in yellow, and we've already been exploring how these are brewed and formed by magma that's got trapped in a magma chamber in a central volcano. This brewing process is quite controversial. On the one hand, you could be sedimenting crystals, so it's a kind of fractional crystallization where you've got your crystals that are falling down through your fluid, and that separation of dense crystals like your egg timer is separating out dense olivines and things like this, and then leaving a more silica-rich magma. That's one model for generating the rhyolite. The other model is that you just melt the rocks that are around this stored magma. And it's the melting model that seems to be taking precedence at the moment. So yes, absolutely, this is being formed in your in and around the magma bodies in central volcanoes. Rhyolitic eruptions are of considerable concern in terms of hazards. They're amongst the most powerful and hazardous eruptions on Earth. For example, the most powerful eruption, well, subaerial eruption of the century so far, Cauye in Chile, was rhyolite. The 20th century, the biggest eruption was rhyolite as well. So we're kind of concerned about rhyolite in terms of explosivity and big volume and creating a lot of ash. What these eruptions do is they seem to start off making pumice, so they're very explosive, and they end up being effusive and creating lava flows. And these are both photos from Torfjökull in Iceland, just north of Katla, which is Iceland's biggest rhyolite field. And lots of my research has been looking at this transition and what controls the style of the rhyolitic eruption. The answer, we think, it's all about how, well, whether the gas can escape from the magma. Because there is dissolved water and CO2 in the magma, that gives it its fizz and encourages violent acceleration and fragmentation to create an ash plume. If you can degas and escape those volatiles from the magma, then it can just be more gently effusive and create lava. And Torfjökull has produced a really big rhyolitic eruption about 75,000 years ago. And when I was a PhD student, my supervisor was Dave McGarvey, who many of you may know. He was a great supervisor, and his own PhD was on Torfjökull as well. And then he supervised me, and then both of us together supervised Jackie, who also worked on Torfjökull. So there's quite a family and generational thing going on here. And what we can see in the top photo here is some lovely flat-topped rhyolitic volcanoes. These are called tuyas, or table mountains, and they're formed when there's an eruption which melts through the surface of a ice sheet. The ice was about 400 meters in thickness, and these flat tops here are lava that's just topping these volcanoes. I worked on this in my PhD, and then Jackie also worked on it, and she was measuring the concentration of water and CO2 in the magma and found out that it was extremely rich in these volatiles, which helped to explain why it was so explosive. But there's something else that's really interesting about this eruption, is that it seemed to have been triggered by Baldabunga. And you're probably thinking, well, that's the wrong part of the country. Because if you look at the map here, Baldabunga is like over a 100 kilometers, 60 miles to the northeast. And what seems to have happened 75,000 years ago is that once again there was magma that was gathering in Baldabunga, and rather than going to the northeast, as it did a few years ago to have the eruption of Holocene that we've just been looking at, instead it went the opposite direction and it went down to the southwest. And this was when a basaltic dike hit a body of rhyolitic magma that was probably quite stagnant and being stored under the volcano. And the dike hitting it gave impetus, heat, and gases as well, and then drove this large volume eruption. So it's kind of interesting how you can have propagation of dikes of basalt either way from Baldabunga with drastically different consequences. I should just finally add on this slide, where my mouse pointer is now, hopefully you can see this. This is Baldabunga in the far, far distance, and the dike would have propagated all the way from there to the foreground here. I personally, in my PhD, worked on those flat-topped volcanoes, and I was trying to work out the style of the eruption, and was quite excited when Harry Pinkerton and myself discovered this kind of thumb of lava sticking up. This was the conduit or the pathway very close to the surface that was feeding lava. This was an obsidian lava flow that was being fed. And we looked at it and well, this looks very strange because it looks like the magma is breaking up. And this looks like a fault to us. So this magma isn't just simply flowing out of the conduit, it's actually breaking up into pieces. And I've then found some interesting textures in thin section like this, where on the one hand, the magma was breaking up into little chunks, but then it seemed like all these chunks were sticking back together again. It's gone like jelly-like if you look on the right-hand side here. It's formed a beautiful ductile flowing flow band now, which is being contorted and folded. And this was very interesting and exciting to find that magma was able to be fracturing as it was rising to the surface, but then healing together again and creating something that was continuous and was an intact lava flow. We then started thinking, well, maybe this could be quite a good way of getting the gas out of it. Because we've got this rhyolite, which is really thick, viscous fluid. Bubbles are stuck in it. It's very difficult for this gas bubble to escape from it. But if you could pulverize the magma, then you've got very small pieces that you could easily dry out and the gas could quickly escape from them. So we started thinking that this could be part of that explanation for how this rhyolite can lose its gas and end up being a effusive lava-producing eruption. And my PhD student, Ellen McGowan, who's now a geology teacher in Sedgwick School, doing great things. Ellen took her work on there a lot further, and she was inferring that at the end of this eruption, we had some fracturing that was taking place of this very thick, viscous magma, and that we'd have had the kind of jetting of ash and gas out of the top at the same time as lavas were being extruded. So we're doing lots of work in this field of how gas is escaping from rhyolitic magma. To go back to that same eruption again, Dave kept on working on it and had a PhD student called Jonathan Moles. This map here shows Torviökull, and those flat-topped volcanoes I just showed you were these ones here. And there were many other similar ones formed at the same time in a big ring all the way around the caldera. So there was a whole load of volcanism taking place from different vents at the same time. There's also a very well-known ignimbrite, so a rhyolite composition ash deposit, like a thick pyroclastic ash deposit in the next valley down, close to places called Thorsmjorg. And this is called the Thorsmjorg ignimbrite, and it's been known about for more than a century. And people have always wondered, where did this come from? And Jonathan Moles did some chemistry and found, remarkably, that it exactly matches Torvijökull. So this eruption of Torvijökull that was triggered by Bárðarbunga didn't only produce what is preserved at that volcano, it also produced really widespread ignimbrites that spread out probably in all different directions. And they're just very locally preserved here because there was no ice at the time. And this means that the volume of this eruption was far larger than we ever thought was possible. This was a colossal eruption of rhyolite only 75,000 years ago. I'm taking on a bit of a whistle-stop tour, and I want to go to Krabbla, and then we're going to go to a couple more places, okay, on rhyolite. And then we're going to finish off in the Icelandic East Fjords with David Attenborough and George Walker. So, Krabbla, as we've mentioned already, is one of these central volcanoes that has a fissure swarm of all these basaltic dykes, which are more or less north-south, and we have our stored magma in a magma chamber here in the center. This is where there's the geothermal zone. And there's a nice dike of rhyolite that's been erupted, which is conveniently called Hrafnarhryggur, which is almost impossible to say, but I somehow managed, which is on this side here. That means Obsidian Ridge. And you can see Obsidian Ridge on this image here that's been produced by some friends at the University of Canterbury in New Zealand. This is the top of a dike, but it erupted into ice, into shallow ice, which then kept all the products in that area. And thankfully, the ice has slightly eroded away the rock from it. So we get a glimpse a little bit deeper down of the dike that fed this rhyolite to the surface. So we've been doing some work on that, and we can go to a depth of almost 100 meters, and we're trying to track the way this rhyolitic magma is moving. But still, 100 meters is quite shallow, really, because the important stuff is going on at a depth of, say, 2 or 3 kilometers. That's where we think that rhyolite is typically stored. So we are kind of scratching the surface. But it's so fascinating, the obsidian from Obsidian Ridge in Krabbla. And I've got a piece of it with me, which I always like to take around. It's such spectacular magma. And it may look to you kind of fairly plain and just kind of black or brown. But if you get thin sections of this, then it is incredible. It's like it's an entire world of texture and complexity. For example, you have different colored bands of obsidian, which have all been smeared out and then faulted and healed back together. Really spectacular flow banding. Perlite, you'll probably know from gardening, if you garden, that is obsidian or pumice, which has soaked up a lot of water. And so we've been studying the way that perlite forms. There's also very strange textures. The bottom middle one here looks like there's lots of corrosion going on, as if there's some chemical attack going on, which is eating away some of this magma. And Annabelle Foster, who's the photo of here, she's a PhD starting in Durham last year. And Annabelle's looking into this fascinating world of texture and complexity, trying to work out exactly what's happening in what superficially looks very simple black obsidian. Anyway, this is still very superficial because we want to go down a bit deeper. Now, I mentioned Krabbla and geothermal, and this is a place where there's been some really leading geothermal power extraction going on since the 1970s. There's something like 38 wells that have been sunk, but the holy grail in the geothermal world is to go supercritical. This is where water is no longer forming simply steam, because it's at such high pressure and temperature, it's more than 370 degrees C and a depth of a couple of kilometers. It means that it forms as a strange different form, which has got a huge energy stored inside it. If you could only tap those fluids, then you could liberate far more energy from your geothermal borehole. It's important because geothermal energy is continuous and it's green. There's no CO2 emissions from this, and also is not dependent on weather conditions at all. So geothermal is a very important energy technology, but you can't make very much energy from one geothermal borehole. That's why people are trying to drill deeper and hotter than before to get more energy per borehole, which means that it has less of an environmental impact of having an eyesore on the surface, as well as being able to get more heat out. So there's a massive project that's been organised by the International Deep Drilling Consortium, and a well was planned to be sunk in Krabbla after years of planning. This takes years of planning to do drilling like this. And after lots of geophysics, looking at gravity and patterns of earthquakes and the heat flow, they decided that this spot here was an excellent place to drill, IDDP1, which is quite close to the Obsidian Ridge and close to a crater called Viti, which means hell. So this hole was sunk in 2009 with the aim to be reaching about 5 kilometers, which is going to be deep enough and hot enough to hit this super critical fluids. They started to drill, and look what happened. You can see here on the bottom left. I'll just play you a few seconds of this video. What you're going to see is that the wellhead, this is the top of the geothermal borehole. And let me just say that's not normal.
The deep drilling borehole turned out to be a magma well, and it was clear that the initial objective of drilling for supercritical geothermal resources wouldn't be achieved. However, new opportunities were created with this new type of well.
Except for one other minor case, it's the only place where people have actually drilled to magma. And to know exactly where the magma is and what the conditions are, and that it's feasible to drill there, is an absolutely incredible and unprecedented thing.
Okay, hopefully you could hear that okay. That was John Eichelberger, who's very much driving what is going on since. So the geothermal drilling accidentally hit rhyolite magma, and the drilling apparatus was lifted about 10 or 11 meters by the sheer pressure that was intercepted when this magma body was hit. It's extremely concerning for many people because there was some of the best geophysics in the world was done here and said there is no magma at shallow depth. That's what we're also saying at Campi Flegrei by Naples, that there's no shallow magma. And yet in Krabbla there was, it was lurking there undetected somehow. And the same could also be true in Campi Flegrei and many other places worldwide. So rhyolite seems to have a way of being stealthy and hiding from geophysical view. What happened when the drill hit magma is that in the drill cuttings that come out, there's lots of mud and nut chips and stuff comes out. Also, they retrieved some pieces of pumice and obsidian. And we are very lucky to be able to get hold of some of this sample, which looks like this. They're maybe 1 or 2 or 3 millimeters across, little chunks of obsidian that was retrieved. This is the only obsidian, or well, the only rhyolitic magma that's been deliberately intercepted. So actually, I should say not deliberately, it's been accidentally intercepted. And there have been some cases also in Menengai in Kenya of similar interceptions by geothermal boreholes of rhyolite. And I'd love to know much more about that because there's also a big story to come out of Menengai. But this is a really special sample to have. And we've been looking at this in a lot of detail, realizing that there were bubbles that were forming when the magma was intercepted. And you can see these bubbles here. These are little tiny gas bubbles that were forming. the magma was frothing up in response, and it was being drawn up off the geothermal borehole like a kind of straw drinking it up. There's also quite a lot of bits of phenocrysts here, so crystals that come from crystalline rock as well, which seem to be getting caught up in all of it. And there's many questions of exactly what this magma was. Was it a large body of liquid magma, or was it a mush, which is mostly solid, and it had a little bit of liquid sitting around between the crystals? But when this straw of the geothermal borehole came down, then a bit like a slush puppy, you were sucking out that liquid from between the crystals. So those are the kind of questions that are being asked. And we had a paper led by Elodie Soban, which came out very recently. And our current model is that we had a body here of older intrusive rock. This is felsite, which is like a fine-grained granite from earlier magma that was stalled in the shallow crust at 2 kilometers depth. And we think it was then hit by a basaltic eruption, by one of these dykes. And the heat from the basaltic magma, plus potentially some of the fluids that were liberated by that heat, then came up and reactivated, they remelted and reactivated this old crystallized material. And that was then the body of magma that was retrieved. If that's the case, it's suggesting that not always when you hit stored underground rhyolite with a basaltic dike, you don't always trigger an enormous, huge eruption at the surface. Sometimes you don't do very much. And if it hadn't been for the borehole fortuitously going down and hitting it, we may never have realized that there was magma there. Anyway, this is like a very interesting story, Krabbler, and there are currently plans afoot to try to now deliberately re-drill into this borehole. That's because it was accidentally drilled into, and the Icelanders did brilliantly to keep calm despite having drilled into an active volcano and into magma. They managed to keep it under control, and for a couple of years it was the hottest geothermal borehole in the world, until eventually it corroded because there were so many corrosive gases that were coming out, volcanic gases, that the kind of drilling kit and the casing of the borehole rather was becoming damaged. So it was cased, it was filled with concrete and just left. But there are plans to try to deliberately drill back into it because we know exactly where the magma is. And this is called KMT, the Krabbler Magma Testbed. And I can put the address of that into the chat a bit later because it's well worth going to. It's a great website. And people are talking in terms of the ultimate frontier of being able to now, rather than going to the stars or to planets, let's go underground to magma. So there's some very ambitious science there to try to deliberately re-drill into the magma and then put all kinds of instruments down to try to understand more what magma does when it's underground. Okay, I don't want to overwhelm you with geology, so we're going to just flip through a few nice places. Essentially, we're going into older rocks now. So we were just then in those previous places in the active rift zones. We'd started off where we were in Baldabunga, which is just in the north here, and then we've been to Katla and Torviokul, which is here, and then to Krabbler. We're now going to go to the older side. So we'll start off on the west, and then we're going to go to the east. And being older means that there's been more erosion, so we can see more deeply inside these volcanic systems. And that's useful because it's giving you a fossil, which is a record of the kind of processes which are taking place now in these central active rift zones. And it's going to a place called Husafell, which is a lovely place with a good campsite and lovely woods, which I recommend going to sometime when we all can fly. And so this is a dissected central volcano. It's a bit like Krabbler, if Krabbler were 2 or 3 million years old and then had glaciers cutting through it. And there's a large number of intrusions here of rhyolite. And we've started studying some of these down in the south end here. We think that it was about a depth of 500 meters. So we're getting now to the business zone of where eruption controlling processes take place. And here's an example of a kind of sheet of rhyolite with lovely obsidian chilled margins, about 3 meters in thickness. This is a place that my PhD student Holly Unwin is doing a lot of work, because we've discovered something quite interesting. It's a hydrofracture, and I'll explain what I mean. There were intrusions of rhyolite rising up, cutting through older rocks, many of which were basalt or tills, but also some strong layers of ignimbrite in previous powerful eruptions. And one of these sheets was trying to rise up. We can actually see it here. It was a sheet of rhyolite that was trying to rise up, but then it hit an extremely strong layer of welded ignimbrite, which behaves like a very dense lava. And it wasn't able to go through there. So locally here, it was an intrusion that was trying to move towards the surface, but was having difficulties because of the strength of the rocks it was failing to fracture through. And what we discovered is that just higher than that strong zone here, there was a grey looking vein that extended for a very long way, for about 40 or 50 meters. And this vein was filled with sediments. And we quickly realized that this was a hydrofracture. So essentially, this is rock that has been fracked. There's been such a high pressure of fluid because of the volcano that it's managed to prise this red layered rock here up by about almost a meter. You can see here on the schematic drawing lower down, this is the hydrofracture here, and it's been propped open by particles of pumice and obsidian that have been injected into it. We find this particularly interesting because it's a fossil of a rhyolitic volcano trying to erupt, but encountering difficulties in that the magma couldn't just simply rise up in a straightforward way. It was hitting a strong barrier, and then it was not able to rise easily. And we think that the pressure was accumulating until it was able to frack its way through the rocks just above. And Holly's been looking in loads of detail at the nature of the sediments that are filling up this hydrofracture. It looks very similar to similar hydrofractures that you form in glacial environments, and also propped hydrofractures from hydrocarbon reservoirs that we've been fracking. They have actually sometimes had proppants put in them, which can have similar sedimentary structures too. It's quite exciting because this tells us that we've had multiple pulses of fluid injecting into a crack. So it's like a musical note that's being repeatedly played, because we're very confident that each time this takes place, you're generating an earthquake. And we very much know that lots of the unrest and the seismicity at volcanoes worldwide is triggered in this way by a hydrofracture having a fluid injecting into it. So Holly's thinking a lot about the number of hydrofracture events, the kind of pressure that might have been involved, wondering what might have been detectable at the surface at the time, and also wondering how much gas might have been siphoned off the magma in it's a kind of blocked valve here, which is blocking up by these particles. And we're anticipating that quite a lot of gas was able to be bleeding out as well. So watch this space. We're doing a lot of work on this at the moment. And absolutely, we think this could be the source of many of these types of volcanic earthquakes that are found, not the tectonic earthquakes that are related to dike formation, more particularly in central volcanoes around magma chambers. And finally, on our whistle stop tour, we're going to go to the East Fjords. Maybe some of you folks have been to the East Fjords. I'm a kind of recent convert, and they're absolutely beautiful. So over on the east, we're in our tertiary rocks here, say between 3 and 9 million years old, and they've been dissected down to a couple of kilometers in places now. This is a lovely corner of Iceland near the town of Höpp, and there's the famous Vesturhorn and Austurhorn, and we'll also go to Slöfredalur. If any of you saw that series with Dave Attenborough last year, I think it was called 7 Worlds, 1 Planet, maybe. He gave the introduction to that from a beach called Stocksness Beach. And the mountain behind him is one of these dissected tertiary central volcanoes, which some of my colleagues are studying to try to investigate how rhyolite is stored and moves in the shallow crust. It's a really beautiful place. And also the East Fjords is where the great George Walker did much of his work. He was the pioneering volcanologist who really founded much of the physical science that volcanology has become. And he did some painstaking fieldwork in eastern Iceland with lots of camping and Icelandic jumpers and things. And part of his seminal work that he did in understanding the plumbing of volcanic systems was to identify zeolites, which are these alteration minerals found down here. And he recognized that zeolites form at different depths in the crust. He then walked over East Iceland finding dissected volcanoes, and he could identify the zeolites and then tell how deep he was in the system. Anyway, I was excited to go to this museum. It's the only museum I've ever been to a volcanologist, which is in Breiðholtsvík. And if you get the chance to go, I really strongly recommend it, because you can find out lots about his life and work and about Icelandic volcanism too. Anyway, this was part of what we call the Magical Mystery Tour, and there's a great group of us, which was led by Steffi Boyschardt of the University of Uppsala, who's done a lot of work in the East Fjords looking at these dissected volcanoes. So for me, this was really exciting to be going down a little bit deeper to maybe 1 or 2 kilometers depth. And behind us here, it's called a laterally called Sandfell. And a laterally is where there's a sill which fattens up greatly on the upper side so that the roof rocks are domed over. And this laterally called Sandfell has massively domed the basaltic lavas on top of it. That was what we were visiting on this day. So it was very exciting for me to be walking with Steffi and team into the heart of one of these central volcanoes that's now, as you can see, got at least 1 kilometer of relief exposed. We're looking here at a Pluton. This is a large volume body of intrusive rhyolite, this pale scree. Looks a bit like a red pike, if I remember where I used to come from. And Steffi's done lots of interesting work reconstructing the organization of the rhyolite and the way that it was making its way upwards, and sometimes trapping and capturing pieces of the country rock that were then falling down into it as roof pendants. Lots of interesting interactions that are going on there at the roofs of these magma chambers that we'll be recording, the kind of thing that we really need to understand volcanic unrest at these kind of restless calderas. Something else that I found amazing was this outcrop at Horn. It's such a beautiful and complex rock, which has got a basaltic end member, which is the dark stuff, and also a rhyolitic end member, which is the palest color material here. And you can just see from the complexity here, it's mind-boggling. There's been so many interactions going on of the 2 magma types. You form hybrid magmas where there's been partial mixing going on, and then those hybrids themselves have been mixed with other hybrids. And this is clearly recording many episodes of interaction between a basalt and rhyolite. You can imagine that there's a kind of sleepy rhyolitic magma chamber that's being repeatedly poked by basaltic dykes trying to wake it up. And it's a question, which time is this magma chamber going to wake up? And we have one of those huge caldera collapse, Higgin-Bright type eruptions. And there's many clues that are going to be frozen into these kind of rocks. And I look forward to working more on these in the near future. And just a final field picture, because it's such a beautiful place, of a little bit further north, near to Egilsstaðir in the East Fjords. This is maybe one of my favourite places in all of Iceland for the geology, called Kvitsakur. And this is a caldera lake. So, maybe not so dissimilar to Langdale or something like that. It's been filled with a rhyolitic ignimbrite. This pale material here is all rhyolitic ignimbrite from powerful rhyolitic explosions that's been dumped into the lake. And you can see even some fossils in there, which I'd love to study more. And then intruding through that, we have such a complex cross-cutting network of basaltic dykes and sills. And we're doing quite a lot of work on this at the moment. So you've had quite a whistle-stop tour there through many different bits of the geology of Iceland. I guess a common theme is that basaltic dykes seem to interact with rhyolitic magma, that rhyolite is difficult to get out of the ground and also difficult to degas. If you can't get rid of the gas, then you have a very explosive eruption. And a very large team of volcanologists from all around the world are each adding their own little bit of the jigsaw puzzle here to try to make sense of what is going on, to hopefully in the future really transform our understanding of these dangerous systems. So there's still so much still to learn, and I guess this is a question that I've got for you all. If you could all put in the chat, what do you think is the next eruption? Which is the next volcano that you think is going to erupt in Iceland? It could be on this list, or you may be left field and you say something completely different, some other Icelandic volcano. So if you could all, in your own time, type which you think is the next one to go. I would have said Hekla, because Hekla erupted almost like clockwork, erupted pretty much every 10 years from 1947 all the way through to 2000. But it's now been 21 years since it erupted. So something's changed to that ticking clock. There's something changed with the Hekla system. And every year that we wait for Hekla to erupt, we know that the brewing is continuing in its bowels, and that the magma composition that comes out is going to be more silica rich, and the eruption is likely to be larger. Right, I will stop there. So I look forward to seeing your predictions of what you think the next one is that's going to erupt in Iceland. Thanks, everyone.
Well, thank you, Hugh. That was a fascinating whistle-stop tour to an area which I'm not very familiar with, and I'm sure it's generated a lot of questions coming in from our audience tonight. There's certainly lots of predictions coming into the chat.
Good.
Yeah, that's filling up fast. So
yeah.
I open up the meeting to our first questioner, whoever that may be. If you could use the raised hand under reactions, I'll see who wants to ask a question, and then you can unmute and put your question to Hugh.
And if you prefer to type a question, then you're really welcome to.
Silence.
I'm just going to type the website. Icelanders like very short web addresses. Maybe it needs to have a www. That's the Krabla Magma testbed website that I recommend taking a look at.
Well, I shall ask a really banal question. I'm sorry, I did enjoy your talk.
Thanks, Chris.
And it is lovely to hear a Cumbrian accent and to have a local talkie. You've apart from your travels, you've stayed quite local, haven't you? I'm afraid that when I was writing my notes, every time you mentioned that volcano, I've just written it as U, short for unpronounceable.
Yeah, okay.
And I just wondered, have you actually learnt to speak Icelandic?
No, not really. I speak a few words, but compared with, compared with the many people for whom English is a second language who are in the UK speaking great, my Icelandic is embarrassing.
Well, your pronunciation of the place names was very impressive.
Well, it's practice, I guess. Yeah. Thank you.
I'm sure we've got experts amongst our viewers who will be able to ask you more intelligent questions.
Chris, I think you're totally wrong that questions from experts are not the ones that I'm looking forward to. People are already too blinkered, and experts don't ask interesting questions.
Okay, well, I'm going to ask another question. Did you say that little lake next to where they did the geothermal drilling in Icelandic,
yes,
it meant hell?
Hell, yes.
Yeah, I think that might have been a clue. As in, how did it get its name? Maybe not a good place to go.
I think you're right. Maybe the Icelanders hundreds of years ago could already sense more than the geophysics could.
Yeah.
Hugh, could I ask you a couple of questions? What geophysical techniques did you use for the prognosis for that well?
The prognosis for the well involved, it wasn't me, it was a big team, mostly of Icelanders. They looked at the location of earthquakes with the idea that earthquakes in a volcano would only be taking place in solid rock, and that if there were a body of liquid magma, then you wouldn't be expecting to get any earthquakes in that volume. And in many places like Kilauea, it's been well documented that you have an aseismic, an earthquake-free volume, which corresponds with where we think the magma is. So that was one of them. There was also magnetotelluric, so looking at the kind of magnetic and conductive properties of the rocks. There are many gravity surveys that were done as well, because rhyolite is slightly less dense than basalt, and people were using that to try to infer the subsurface structure. There was all kinds of other bits of evidence that was all put together, including clues from other boreholes that had been sunk in the vicinity. One of them actually had hit rhyolite as well, but that only really came to light afterwards. So it's extremely interesting why that rhyolite could not be detected by geophysics. Why do you think it was
I was thinking the resolution on lots of those tools is not very good. Not enough for a prognosis for a drilling into a magma chamber. I mean, it's hairy stuff.
Yeah, I mean, if the resolution was, say, plus or minus 20 meters, then you could potentially have a 20-meter thick body of magma which could extend over kilometers, and that could be a fairly large volume. It's one of those questions that we're really asking: is how deep is the body of magma? Because when the drill hit it, the drill bit was kind of rotating and trying to drill into the rock, and then it hit something kind of thick and gooey and got stuck. It was then taken out again, and they tried again, and a third time. They couldn't drill actually properly through it to see what was on the other side. And that's one of the objectives of KMT, would be to try to properly drill into it and get the entire cross section so we know how thick it is too.
Did they have any tools in the drill string measuring as they drilled, or was it just on mud returns?
They did have quite a lot of tools, yeah. They were able to measure the pressure. So they had the kind of standby pressure, and they had the temperature being sensed as well. And KMT is talking about a lot more sensors down at the bottom of the borehole. It's really difficult to get things that aren't going to be damaged and just wrecked by the high temperatures.
Yeah.
So there's a lot of people who do sensor development in extreme environments, and they want to become part of KMT to really help us have instruments that are not going to be ruined.
Just one last question. What was the bottom hole temperature and pressure? that you measured the last pressure?
Oh, you put me on the spot. I can't remember. It was something like 12 megapascals. I'm sorry, I don't do bars nor kilobars, I'm afraid. I'm all metric. And the temperature, I think it ended up being about 450 degrees Celsius in the bottom of the well.
Wow.
And that's way hotter than any other geothermal borehole.
Yeah. Thanks.
Thank you. John Wood, you have your hand up, I can see.
Thank you. Yes, Hugh, we all seem to be focused on this same thing, actually, because it's quite intriguing drilling into a magma chamber. What sort of diameter are these holes that are drilled?
Roughly the same as this flask.
Right, okay.
So yeah, like think of like a typical mug or flask, that kind of thing. You start off with a much wider hole, and then progressively you go to thinner and thinner casing.
And there aren't any unforeseen, well, I suppose if they're unforeseen, but unforeseen consequences of drilling into a magma chamber.
What do you think might happen?
Well, I don't know. It blew the top off the well, so could it do anything more dramatic?
That's a really good question. It almost blew the top off the well. They somehow managed to keep it without complete failure, which is remarkable. I guess potentially you might get a runaway effect. So potentially, if you started to fracture the magma, then you could make a big surface area, and then if the geothermal drilling fluids got into that surface area, then you'd be flashing to steam, and you might have a really quite intense explosion. It would depend on the access of the water to get into where the magma is. The actual hole itself is not really big enough to have a powerful eruption coming through. To have a powerful eruption, you need to have a pathway that's at least 20, 30 meters wide.
Yeah.
But there's the question of whether you could start to quarry and impart that kind of damage to the wall of this borehole that could be triggering that. Something else that might happen is that you might inadvertently encourage a lot of volcanic gases to escape. And that may include things like arsenic and mercury and various poisonous species. This is all something that's been looked at in detail by human geographers and social scientists. So people in Lancaster have been doing interviews with drillers about their perception of risk. And also they've been speaking to local school children, just local professionals, and even the local mayor. So there's a lot of discussion that needs to be done about whether the risks are worth it, and also about who is exposed to these risks. In the case of Iceland, people are very kind of tech savvy, and it's a very small population. But if people try to do something similar in a place with a very dense population, then many people may not be party to this kind of experimentation, kind of like really playing God and poking a volcano that they live on. So there's a lot of interesting discussions there.
Hugh, there's a question from Fred Owen. Fred?
Just on mute. Hi, on that sample you had of basalt in rhyolite, what sort of condition would the rhyolite be in there? Was it there as a mush, as a crystal, or was it semi-solid? And how does, presumably the basalt will be about 1,200 degrees centigrade when it gets in there. How does it actually react with the rhyolite within the chamber? In terms of mass transfer and heat transfer, it seems to stay there as a globule. Why doesn't it actually disperse and melt the rhyolite?
That is an excellent question. That's exactly the question that we're starting to ask. I don't have any particular answers to you. We are playing around with some ideas that in some cases the rhyolite may actually be fragmental. And then there may be particles of rhyolite that are then welding back together. So there's the possibility that a basaltic injection may actually fragment this rhyolite. The rhyolite is going to be at significantly lower temperature And when the basalt is injected into it, the basalt is going to be freezing and crystallizing.
Well, what's the temperature difference? What temperature is the rhyolite at?
Rhyolite's at about 900.
Probably it's got interstitial fluid in there as well, so it's not entirely solid, presumably.
The rhyolite's typically going to be about something like 800 to 900. And then if there is basalt coming in, it's going to be significantly heated from that. But its viscosity, even if it were purely melted with no crystals, its viscosity is much higher than the viscosity of the basalt. So straight away, you'd be having the basalt being more mobile and moving around blobs of rhyolite. But we also see the other way around, that we see basalt which has been invaded by these quite sharp, very thin veins of rhyolite. And that poses questions as to how something so monumentally viscous could manage to finger its way into such tiny cracks.
Yeah.
So, I mean, there's so many open questions there that need to be looked at.
There's a question in the chat, Hugh, from Maggie Dietrich. The question was, when is Vesuvius going to erupt? Any clues from Iceland?
I mean, it was last 1944. The Italian team from INGV, they're very much some of the people driving the work in Krabla. So there's a big consortium of Italian volcanologists who are working on Campi Flegrei around Naples, and they're very much part of what is going on there. A team, from near Naples is doing measurements at Krabla. I don't think that we can answer that question. I think we're still a long way off gaining the understanding that we need. We don't really know the amount of precursory unrest that's going to take place at Vesuvius. And that's something that I really probably should have mentioned at the beginning and failed to, which is that 9 out of 10 episodes of volcanic unrest don't end up with a volcanic eruption. So 90% of the time, there may be some clues of rocks breaking and magma moving, and nothing comes to the surface. There's therefore obviously a very high probability that at Vesuvius there's going to be unrest taking place. There could be some upward deformation of the caldera, showing that there are fluids being injected, and there could be an increase in heat flux and gases. That doesn't necessarily mean that there's going to be an eruption taking place. It's that question of, when do we know for sure that there's no turning back for that rising magma? It might just hit a layer of exceptionally strong cap rock, like we saw at Husafell, and then it becomes blocked and fails to rise any further. So, I mean, there's a lot of work that needs to be done to understand that question about Vesuvius.
Okay. Does anybody have any more questions for Hugh?
Yes, could I ask one, please?
Yes.
Could you just recap, please, Hugh, how those rhyolite tabletop formations are made?
Of course, yes. What we think is happening, I don't have a diagram to hand, so I'm going to try and gesticulate for you. What we think is happening is that there's an eruption of rhyolite or basalt under a thick ice sheet. And actually, I can try and draw this for you. We just this paper. This is the beauty of a Zoom call. Excuse the horrible drawing. So there's an option that is through thick ice, and when you melt through the surface of the ice, then you have an explosion may take place, and then there's a zone here where you could have lava accumulating inside an ice cauldron. If you then melt away the ice, you're left with a flat top. The reason why the sides are so steep is because of confinement. Essentially, it's being erupted into an ice cave. Yeah. So there are steep ice walls that are holding everything together. But once you melt through to the top, there's no longer that confinement. And the top surface of most lavas is reasonably flat. So that's why we're forming what's called a tuya, or a table mountain.
Okay, thank you.
We have another question, this time from Audrey.
Yes, I couldn't see my hand. I was putting it up and now I couldn't see it. Right, first of all, I saw a tuya in Antarctica. On the coast of one of the islands of the Antarctic Peninsula this time last year, so I know what they look like with a flat top and some special way that the lava collects. However, what I was going to ask was, there are lots of us here who've been at Open University summer schools in various guises, and we always got the students to do a calculation about how quickly a dike might propagate. You've actually seen a real dike really propagating, haven't you? So that one that went 50 kilometers from the volcano that begins with B and ends in
Bunker. Yes, yes.
How fast did it actually go?
Hi, you put me on the spot there. So it's moving about 50 kilometers. And how long was that? Maybe 3 weeks or so. So roughly
Okay.
2.5 kilometers a day.
Okay,
So,
we kind of came up with walking speed. But
that sounds like good.
It wouldn't be going that fast, would it?
That's more like crawling speed, I guess.
Yeah, that's all right. Still, we weren't an order of magnitude out, really, were we? So that's okay. Great.
No, not at all. No, I mean, I guess it's more like my 4-year-old who walks at a reasonable speed and then stops for a couple of hours.
Yeah.
I guess overall that comes out to similar speed. Which tuya did you see in Antarctica? This sounds incredible.
Oh, I'm afraid I'd have to look it up. But this gives me a chance. In a fortnight, on the Wednesday, in a fortnight's time, for anybody who'd like to come, I'm going to do my Antarctica tour. It's not got much geology in. Well, there's some nice glaciers. It's mostly penguins and stuff. But I was there just a year ago, exactly now. So January last year. And I've got a nice slideshow. So if you'd like to see it here in a fortnight's time, I'm going to run through it for anybody who'd like to see it. So we'll send a proper invitation round to the Westmoreland Society, and anybody else will probably get to know one way or another. But it won't be geology, it'll just be a fun kind of hour of pictures. Say plenty of okay.
Thanks, Audrey.
Yeah, thanks.
You got your free plug in there. It's supposed to be questions,
Like,
not self-promotion. You know, the first question you're going to get next in a couple of weeks will be, what's the name of that tuya?
Yeah, I'll look it up.
Oh, yeah, hey, there's some questions on the chat that I've missed, I think, here. Hi, Kennedy. The term Ignibright. It's a product of a pyroclastic density current. So that's even more jargon. So it's a mixture of ash, which is usually quite poorly sorted, which has been dumped from a dense current. So it's very different from ashfall from a plume. It's been a dense mixture of pyroclasts and gas, which is cascaded down the sides of the volcano. And many in Iceland are several meters in thickness. Okay, so in terms of the vote, we're getting Grim's vote. I think quite sensible. Askia, yeah, Askia is lake filled. That would be a good one. Actually, last erupted in 1961. Hekla, okay. Yep, Hekla I could see erupting. It's definitely overdue if you believe that's kind of the decadal rhythm that it maintained for 50 years. Balverbunker again, okay, I like that. Lots of Grimsville. Katla, well, I would actually love Katla to be the next one, selfishly. But let's see, because it potentially might have erupted in 1999, just that we're not really sure. Eyjafjallajökull's not finished yet. I think on balance here, it's either Hecla or Grimsvötn between you folks. So I think you're wise.
Okay. Well, Chris, can I hand it over to you?
Well, yeah, thank you very much. Yes, for a vote of thanks. Well, I sort of half started my vote of thanks to get the questions going. Thank you very much for a super talk, and I think that's reflected in the comments that people are making on the chat there, that they've really enjoyed your talk. I have to say, I was really surprised at how young you are. I was expecting someone a lot older, and he suddenly appeared, and oh, he's really young. This is unusual for us.
That's the special Zoom filter, okay?
Ah, well, I only heard about the enhancement one today. You've been using that, have you? It clearly works. I've just picked out a few of the things that I liked about your talk. I particularly like the idea of a bucket full of magma, that, you know, the smallest amount of magma. Great illustrations and some beautiful photos. I went with my daughter to Iceland in February, but your pictures certainly make me think, oh, I really ought to go back in summer, you know, especially some of those photos from the east. They were very, my geology does tend to be, I like pretty rocks. So that was very pretty. And of course your obsidian really impressed me. Those slides of the obsidian, particularly beautiful. I think it's lovely, just the black glassy look to it as well. I was reassured right at the start when you said you'd checked the data and it didn't look like there was going to be a major eruption today. So, you know, that was pretty good, yeah. And as some of the questioners have brought up, things like the distance the magma had travelled, you know, quite amazing. And I also liked some of your references, particularly your local ones. So the methane and the cows in Lancashire, I thought was very well done. So that's just a little highlights that I pulled out anyway. And I think you had some great questions once people got going. So thank you very much, Hugh. That was super. And we can all clap. You might just be able to see us clapping.
If anyone has any more questions, thank you so much, Chris. That's really generous of you, and thank you for everything you said. If anyone's got any more questions, then I'm not spelling my own name right. Wait a sec. And that's my email. If you would, if anyone wants to send any more questions, we're very happy to hear from you. I need to get my online lecture done for tomorrow before I answer anyone, though. Okay.
Well, I'll just say thanks again, Hugh, for taking this valuable time out of your busy schedule and giving us this excellent talk. I can say that you've broken all records for Westmoreland Geological Society lectures. We had, at the high point, 91 people listening to you this evening. So congratulations on being the biggest crowd puller Westmoreland Geological Society has had.
Well, that's well, thank you so much, everyone, for being here. And let's hope that Storm Christoph hasn't made too much havoc outdoors when you get up tomorrow morning.
Yeah. Okay. All right. Well, I'll leave the meeting open for those members who want to socialize and catch up with friends that they may not have seen for a while or whatever. And yeah, I'll just leave it running till you all fall asleep or leave or go home. All right? So, cheers, Hugh. Thank you very much.
Bye.
Bye, everyone.